Hi guys, this is Craig Robertson with Innovation Plaza at UNM in the Electrical and Computer Engineering building. I want to do a tutorial to show how to change a 3-to-1 mux into a 2-to-1 mux. And the reason we do this is because with a 3-to-1 mux, you may have a mux that looks like this. And it would have 3 select lines. In this case, right here, A, B, and C. So A, B, and C. And then you'd have 2 to the third, which is 8. So 1, 2, 3, 4, 5, 6, 7, 8. And then one select line out, and these would all be 1s or 0s or whatever, and then you'd select it with A, B, and C. Well, the problem with that is this is 8 pins here. That's another 3 pins, so that's 12. This is 13. So you need at least a 13-pin device, and then more because it's the inner workings of the transistors. But that's a lot of pins. So this translates. This is bad because it translates to more money, and it translates to size. In electrical circuits, they need to be able to fit on, an iPhone or something like that. If you build it all like silly little functions like this that are only 3 variables, if you have to use a huge mux like that to simplify those, then it's just you're using way too much hardware to do what a little bit of hardware can handle, and your circuit gets more expensive, it gets larger, and it wastes more energy. So I'm going to teach you how to change a 3-to-1 like this into a simple little 2-to-1 with only 2 select lines and 4 inputs. So this is where we're at now. That's bad. This is where we want to go, and we want that to be F. And this will be good because this means that we're using less materials, and we're using less power, we're using less size, and this is really, the gateway to good design here. So let's go ahead and look at our equation here. It's f of a, b, c, 3 variables, is the sum of minterms 2, 3, 4, and 7. Now what I'm going to do is I'm just going to go ahead and put them in a truth table. And what I want to do is I want to eliminate c, because I think that'll be the easiest one to eliminate here, and I'll show you why. A, b, and c. 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1. Now, because I lined them up like this, this will allow me to see that this is actually minterm 0 here, and then it will just count down minterm 0, 1, 2, 3, 4, 5, 6, 7. So there's 8 possibilities, 0 through 7, because we 0 index. And I'm going to go ahead and put the F here. And so we know that from this equation, we know that sum of minterms, that means that there's a 1 on these minterms. So let's go ahead and say 0, 1, 2, that'll be a 1. 3, that'll be a 1. 4, that will be a 1. And 7, 5, 6, 7, that will be a 1. The rest of these, since they're not labeled in the sum of minterms, and we know they're not don't cares, those are going to be zeros. Now what I'm going to teach you is I'm going to teach you how to take it from this to this. So what we're going to end up doing here is we're going to say, we're going to take it where C is changing. So C is going to be kind of our, what we're going to do is we're going to put F in terms of C. So I'm going to draw just like a little dotted line right here. Well, maybe a dotted line isn't the best, huh? I'll do a solid line. That way I don't think that they're all 1s. So I'll do a solid line right there, and then I'll draw some lines this way. And I'll split it up so that we can see whether C is 0 or 1 for each of these cases. And as you can see, what I've done here is A and B don't change in these blocks, right? It's AB is 0, 0, 0, 1, 1, 0, or 1, 1. Now what I'm doing is, the only difference here is C. So A and B will be 0, 0, and then we just have to put F in terms of C, whether C is 0 or a 1. So let's go ahead and do this. Let's call these intermediate minterms. That's what I'm going to call them. So I'm going to call this one I0 because 0, 0 is decimal 0. So I'm going to go ahead and call that intermediate minterm 0. Now I'm going to call this one intermediate minterm 1 because of 0, 1. And this one is 1, 0, so you guessed it. It's intermediate minterm 2. This one is 1, 1, so you guessed it. It's intermediate minterm 3. So now what we can do is we can put F in terms of C by using the select lines of A and B. And I'll show you how we do this. Right here we have F is 0, 0. And it doesn't matter whether C is a 0 or a 1, F is always going to be 0 or is going to always be 0, right? So what we can say is when A and B are 0 for our intermediate minterm 0, it doesn't matter whether C is a 0 or a 1, it's always going to be 0. So that's this intermediate minterm taken care of. Now, if A and B are 0, 1, that's intermediate minterm 1, then F is always 1, and it doesn't matter what C is, 0 or 1, right? So we're just going to call this one 1. Now here's where it gets a little tricky, and here's where we have to put it in terms of C. So far it's been just like a normal mux, just reduced, right? But here's where it gets a little tricky, because we're not 1s, we're not 0s, we're a little different. But you'll get the key of it, or you'll get the hang of it in just a second here once I show you. It's for 1, 0, that's intermediate minterm 2. We know that when C is 0, F is 1. And we know that when C is 1, F is 0. So if we put F in terms of C, we can actually just say that F equals C naught. Because when C is a 0, F's a 1. When C is 1, F is 0. And that's only when A and B are 1 and 0, right? So let's try this on the next one. Let's see what the next one does for us. When 1, 1, when A and B equal 1 and 1, that's intermediate minterm 3, we can see that C equals 0, 1. Well, when C equals 0, F equals 0. And when C equals 1, F equals 1. So what will we say that F equals for C? We would just say that F equals C, right? Because it's exactly the same as these little two entries here. That's our output. So when we look at this, and we look at our select lines of A and B, and then we say 0, 0, 0, 1, 1, 0, and 1, 1, instead of just putting 1s and 0s on the end like we would up here, we would just say, 1, 0, and then 1, 1, and that would be our mux. Well, that doesn't do us much good, but down here, we can say, alright, these are our intermediate minterms, 0, 0, minterm 0, or intermediate minterm 0. So we know that that equals 0. Now when we know that we have intermediate minterm 0, 1, intermediate minterm 0, 1 equals 1. Now when we have 1, 0, that's intermediate minterm 2, we know that it just equals C naught under these select terms. And then our last one, 1, 1, intermediate minterm 3, F would equal C. So you can see here that what we've done is we've taken this huge, 8 to 1 mux, and then we turned it into a 2, or into a 4 to 1 mux. So this is a super simple way of reducing a function that allows us to make it good and less expensive, and it's smaller. So we can fit a lot more of these on a computer chip than we can these. So what we did right there is we just saved ourselves a variable, and we used a very smart way to save us space, energy, and money. And that's really what engineering is all about, right? So, employ this method. If you have any questions, come and see us in Innovation Plaza on the 3rd floor of the ECE building. I'm Craig Robertson, and good luck studying, guys.